So, we have been talking recently about empirical formulae for compounds, namely formulae that have a lowest whole number ratio of the different elements in the compound. But we've also talked about molecular formulae, and a molecular formula is much more specific than an empirical formula. These are all examples right here of molecular formulae because carbon dioxide and hydrazine and ammonia and hexene and glucose are all molecular compounds. They don't have metals in their formula anywhere. They're not ionic. These atoms are held together by covalent bonds, as are these 6 atoms. These 4 atoms are held together by covalent bonds. These 18 and these 24 are each held together by covalent bonds as well. These are molecules. And the molecular formula not only tells you a ratio of atoms, it also tells you exactly how many of each atom are in a molecule. In this molecule of hexene, for instance, there are 6 carbon atoms and 12 hydrogen atoms. And yet, the empirical formula for that molecule is simply CH2. So you see, the empirical ratio would give me the ratio of the atoms that make up the compound, but the molecular formula has more information. It tells me exactly how many of each atom and the ratio, which I can see is 1 to 2. So it's a much more informative piece of information. Now, don't get carried away. Some molecular formulae, like the 3-atom molecule CO2, carbon dioxide, the empirical and molecular formulae are the same because this is the formula for a molecule of CO2, and it just happens to be a lowest whole number ratio. So some molecular formulae can be empirical, while others, like for hydrazine, are not empirical. Sure, this tells me a molecule has 2 nitrogens and 4 hydrogens, but the empirical ratio or empirical formula is only NH2. Ammonia's molecular formula is empirical. There's no lower whole number ratio than 1 to 3. But glucose, one of the many sugars or carbohydrates as we call them, has the empirical formula CH2O. And that's why they're called carbohydrates. All your most common carbohydrate molecules have an empirical ratio of 1 carbon to 2 hydrogens and an oxygen, and that's why they're called carbohydrates. In any event, we need to know this information if we want to convert or calculate what a molecular formula is when we're given nothing but the empirical formula. And before we can do that, we need to make sure we understand 2 terms. We have been talking about molecular masses for some time. Namely, those are the masses of molecules. And clearly here, if I look at ethene, we have a mass of 28, 2 times 12 plus 4 times 1. 3 times 12 plus 6 times 1 gives me a mass of a molecule of propene as 42. The molecular mass of butene is 56, and that of pentene is 70. But notice that every one of these molecules has the same empirical formula. They are all CH2 in their empirical formula. Now, consequently, we have spent a great deal of time learning how to calculate empirical formulae by doing analysis of the compound and converting masses of each element to moles and using the lowest whole number ratio to get the empirical formula. Well, now we can use this piece of information along with this piece of information, molecular mass, to determine exactly what the molecular formula is. For instance, if I said that I had a compound with a empirical formula of CH2 and a molecular mass of 56 atomic mass units, I could easily calculate what the molecular formula is, and here's how. The empirical ratio has a mass. 12 plus 2 times 1 is 14 atomic mass units. And we call this mass, since this is not a molecule, we call this mass the empirical mass. It's simply the mass of the empirical formula. And notice that all of these compounds that share the same empirical formula all have molecular masses, masses of the molecules, that are multiples of the empirical mass. And that should make perfect sense too, because after all, the only difference between this empirical formula and this molecular formula is we have twice as many of each atom. And therefore, it makes sense that the sum of all the atoms should be twice as great as the empirical mass. 3 times as many atoms, 3 times the empirical mass, and so forth. So, knowing just the empirical formula and the molecular mass, I can deduce the molecular formula, because from the empirical formula, I can get the empirical mass by simply looking up atomic masses. And I know that the empirical mass and the molecular mass are related as multiples. The molecular mass will always be a multiple of the empirical mass. Now, sometimes it might be the same, but that is a multiple. That's 1 if the molecular mass and empirical mass are the same. And that's trying to tell you that the empirical formula is the molecular formula. But in this case, since the molecular mass is 4 times bigger than the empirical mass, it means that whatever the molecular formula is, there are 4 times more of each atom. And so I would simply increase all the atomic numbers by 4. And we're clearly talking about butene. So yes, with an empirical formula, you can get an empirical mass. And once you know the molecular mass, you know it's a multiple of the empirical mass, and you will know what multiple the molecular formula is of the empirical formula.